The next thing we're going to talk about is area of a trapezoid. This is used in Riemann sums as well as rectangles. Now, we know that the rectangles did kind of a bad job sometimes of really fitting into that shape of that curve. So what we're going to try this time is instead of rectangles, we're going to try and make trapezoids. So we're going to connect this point here at the edge, the left edge, to this point here, which is the right edge. So just make a straight line there. Now, of course, that straight line is not going to exactly follow the curve. It's going to be a straight line, but it's really, really close to what it's supposed to be instead of way above and then below the curve. So let's see what trapezoids can do for us. Let's start by figuring out what is the area formula for a trapezoid. How do you find that area? This is something that you did back in a geometry class. A trapezoid has two sides that are parallel to each other. Those are called the bases. So this will be like base 1 and base 2. It doesn't matter which one's which. Okay. Now, to find the area of a trapezoid, you need to know both of those base lengths, and then you also need to know the height of the trapezoid, h. We're going to be dealing with what are called right trapezoids, meaning that this angle is a right angle, and of course, since both of these are parallel, this is going to be a right angle as well. This is going to be at a different angle that is not a 90-degree angle. That's how you have a trapezoid. Exactly two of the sides are parallel. Okay, so we just need to figure out how long each base is and what that height is. In order to figure out the area, we need to figure out the average base length. Because really, if we figure out this length, we can take this little triangle right here and flip it over, I guess rotate it over here so that it fills up this space. So the average between those two base lengths would be the length of basically that midpoint. And then you just multiply that times the height. So here's how you find area of a trapezoid. A equals base 1 plus base 2 divided by 2. That's the average base length times the height of that trapezoid, which is this. Now, when we draw those rectangles or trapezoids or whatever, the height is going to be along the x-axis, and the parallel sides are going to be those vertical lines. So this is not exactly what our shape is going to look like. We're going to rotate it so that the trapezoid looks like this. So this is our x values, x1 and x2, and then the base lengths are going to be the y values. So this is going to be like f of x1, and this is f of x2. So we can rewrite that formula that we had. Instead of base 1 plus base 2 over 2, its area equals f of x1 plus f of x2 over 2 times the height, which is the change in x. How far apart are the x's, that distance? So that's what we're going to be doing. We are on approximation number 9, trapezoidal Riemann sums with intervals of length 2 units. I've already got the drawing done out with the yellow and everything. Okay. So here we go. Area equals a half times the height times base 1 plus base 2. We are making the heights of the trapezoids be 2 units. And again, the height is not really like up. The height is the change in the x's. So 2 units is going to be from 1 to 3, and then from 5 to 7. 1 to 3, 3 to 5, 5 to 7. So h is going to be 2. A equals 1/2 times 2 times, and then we need to figure out the this distance, those bases. So our first trapezoid is going to go from here to here. Go ahead and make that guy blue. So that is definitely an under approximation because we don't have any area that is outside of our curve. Our second trapezoid, so we connect the left side and we connect the right side and then draw a straight line. This guy is also an under approximation because all of the blue is overlap. There's nothing outside of that curve area. And our third one, this one's a little bit harder to draw because that curve is so close. Okay, there's technically like a tiny amount of yellow that is still under there. I know it's not going to show up very well in this video, but yellow, yellow, tiny bit of yellow. So this is an under approximation, but it is darn close to what it's supposed to be. Okay, we remember that we need to find the areas of all three of those trapezoids. So our first trapezoid is going to be 1/2 times 2 times the difference between the bases. So f of 1 plus f of 3, because those are the two x values. You cannot see what I am writing. Ta-da! Okay, so this is our first trapezoid. Between x equals 1 and x equals 3, we find the average by adding the two y values, because that finds the bases. The 1/2 divides that by 2 to find the average between them, and then this 2 was the distance between 1 and 3. Okay, so that was trapezoid number 1. Trapezoid number 2. We still have to do the average, so find the 1/2 there. 2 is that distance between your x's. We're going to do f of 3 plus f of 5 because 3 and 5 were the x values there. Plus 1/2 times 2 times f of something. Okay, our last trapezoid goes from x equals 5 to x equals 7. And there we are. Now, hopefully you guys can see there's some commonalities. So that 1/2 shows up in every single one of these trapezoids. It's going to show up in every single one every time. So you could, if you wanted, factor that 1/2 out. Also, because the heights, the distance between those x's is the same every time, you could factor out the 2. Now, maybe you notice that 1/2 times 2 is 1, so they cancel out anyway. But you do have that option to factor out the 1/2 and factor out that distance. Okay. So now it looks like all we're doing to find the area of everything all together is adding up all of those f of x's. So f of 1, we've already made this table. 1 is 6.6 repeating, so that was that, 20 over 3, plus f of 3 is 8, which is 24 over 3. F of 3 is 24 over 3 again. F of 5, 20 over 3. F of 5, 20 over 3. And f of 7 is 8 over 3. Yeah. All right, so we just add them all up by adding all the numerators and keeping it over 3. 20, 20, 20 is 60, 70, 80, 90, 100. And 8 twice, so 116 over 3, which is 38.667 calculus, so 3 decimals, or leave it as a fraction, I don't care. Okay, that is a much closer under approximation than that right-hand Riemann sum that we did a little while ago. The right-hand Riemann sums were definitely under approximations because there was more leftover yellow than there was leftover blue. Okay, more underage than overage is another way to say it. All right. On the back, it's a very, very similar type of problem. I'm going to go ahead and draw those trapezoids. Figured out that I draw neater this way. Oh my goodness, so much better. Okay, what's kind of nice about the trapezoid sums is that every single side, like the bases, all touch that f of x function. All touch it. So you're not like trying to figure out, am I supposed to do the left or supposed to do the right? You use both. Okay, so these little line segments are slightly underneath, exaggerated a little bit. They're just very slightly underneath. So you can see this, and there's another one in there somewhere, whatever. Teeny tiny amounts of yellow and everything else would be overlap. To find the area of one trapezoid, it's going to be 1/2 times, and then the height of each trapezoid is 1 times, and then base 1 plus base 2. Base 1 is f of 1, base 2 is f of 2. When you find the heights of the second trapezoid, they're going to be f of 2 and f of 3. Now, you might notice that they will have the same 1/2 and they have the same 1 as the height. So you could factor that out and then just like add all of your heights together. Okay, so that will save you a lot of extra work. And you might notice that the f of 2 is going to show up twice. F of 3 is going to show up twice because f of 2 is the big base for the first trapezoid and it's the small base for the second trapezoid. So you get lots of repeats. There's more stuff in here, but I'm not going to take up more video time with it. Okay, so I would definitely get that factored out, the 1/2 and the height. And then you just add up all the bases. Make sure you get the outside ones once and make sure you get all of the inside bases twice because they get used for 2 different trapezoids. I have written out all of the answers to all of those numerical approximations. The 0.667, those are all your 2/3. If you want to pause this and then copy this stuff down, go for it. You are welcome to work out all those problems on your own and then know that these are the correct answers. Okay. Over approximations means there's more shading from the rectangles than there was supposed to be underneath the area of that curve. All right, let's go ahead and keep going. At this point, place a star next to the approximation that you feel is the most accurate to the actual area. Okay, so we want the smallest number from all of the over estimates. Smallest number from all of the over estimates, and I think that's this one. 40.167 is less than this one. Ooh, oh, that's under. I got so excited there for a second. Over. Yep, this is the smallest because both of those trapezoids were under. And then let's find the highest value of all of the under approximations. So between these 3 and these bottom 2, the highest value was 3.9667. So you might notice the more rectangles or the more trapezoids that we had, the closer we ended up getting to, looks like 40. So probably we are going to have 40 as the correct answer for the area under the curve. Area actually about 40 units squared. Probably. Okay, we will come back to this space later on, this page 487, to figure out how we actually get the correct area. But we have to do some extra work and learn some extra stuff before that. I'm going to show you guys how to do now the same Riemann sums, but this time you're going to be given tables instead of graphs. And I think you're going to like this better because you don't have to like plug a function into your calculator. We are going to approximate each definite integral by finding the indicated Riemann sum, and they also tell us how many intervals we're going to have. Okay, we've got a couple of definitions here. This 0 means the left boundary, and the 25 means the right boundary. The f of x values are those y values, those, I'm going to call them heights, like how high up what this distance is, that vertical distance. Okay, and we're given some x values. So we are still looking for what is the area that is between f of x and the x-axis. And we start at x equals 0 and end at x equals 25. And you can see the 0 and the 25 x values on here. We're going to be using a midpoint sum. So we are going to use the left and the right, and we find what is halfway in between them and use that y value. Okay, if you need to see an example of that, go back to approximations numbers 7 and 8. That's when we did Riemann sums of midpoints. Okay, 3 sub-intervals. So we want to take from 0 to 25 and divide it up into 3 intervals of the best, like most similar size that we can. So from 0 to 25, it looks like we can separate it at 7 and 15. So one rectangle will go from 0 to 7, one rectangle will go from 7 to 15, and one rectangle will go from 15 to 25. Okay, so these are my rectangles. Okay, before they went from like 1 to 3, 3 to 5, 5 to 7, and this is how they're separated out this time. We are doing 3 subintervals, 1, 2, 3 rectangles. Okay, so now we just need to find the areas of those rectangles. Rectangle 1, 2, and 3. So the area will equal the area, which is the like change in x, and then the y value. So we need like the width across, and we need the height up, plus the area of the next one, plus the area of the last one. Okay. The x value that we are going to pick is the one that is halfway in between the other 2 values. Now, these are not perfectly like evenly spread out, and they really can't be, because 0 to 25, like that distance is not divisible by 3. So we just do the best we can based on the information they give us. So the number that is like half-ish way between 0 and 7 is 4. That is the x value that we're going to pay attention to, and that has a height of 6. Okay, so this is like when we drew that dotted line straight up from the center. So 6 is the height of our first rectangle. Oh, I just put h. Good job, me. 6 is that height, and the distance between 0 and 7 is 7. So that's like our change in x. Over here, from 7 to 15, that has a distance of 8. Okay, so across your x-axis, you're just going 8. And the middle-ish of that is 12, which has a height of -10. We'll talk about negative areas in the future. Don't worry about it. It's going to be a negative number. Just go with it. Next one, from 15 to 25, about halfway, well, actually halfway this time, is 20, and that y value is 8. So that's the height of that rectangle. And the distance between 15 and 25 is 10. So math it up. 6 times 7 is 42. 42 minus 80 plus 80. Oh, wow, I could have saved myself some effort there because these guys are opposites, so that reduces to 42. Okay, B, from 0 to 15. So we're starting at 0 and ending at 15, which means we do not care about those last guys. We are using 4 sub-intervals. So it looks like we're going to go from 0 to 4, 4 to 7, 7 to 12, and 12 to 15. We're using a left-hand sum. So we are always going to be using the left side of each of our rectangles. The y value of the left side. Okay, so from 0 to 4, we're going to pick 15. From 4 to 7, we're going to pick 6. From 7 to 12, we're going to pick -5. And from 12 to 15, we're going to pick -10, because we're always using the left-hand side. Notice that sad little right-hand endpoint. We're not going to use it. Okay. So what are our distances between our x values? This one is 4, this one is 3, this one is 5, and this one is 3. Just finding the difference between those two numbers using subtraction. Okay, so the area between x equals 0 and x equals 15 is 4 for that width times that height of 15. 4 times, I guess I'll do it in the same order that I did on the last one. 15 times 4 plus 6 times 3 plus -5 times 5 plus -10 times 3. So if you draw these little rectangles out, kind of like I'm doing, I've got a rectangle between 0 and 4. It has a width of 4, and then circle the height, and you've got it. So let's see, I've got 15 times 4 plus 6 times 3 plus -5 times 5 minus 10 times 3. I get 23 for that area. Cool. C, approximate from 4 to 20 using a right-hand sum and 4 subintervals. So they really have to give you 5 points if you're doing 4 subintervals. They're just gonna do it. Okay, so from 4 to 7, we're using the right hand. From 7 to 12, we're using the right hand. 12 to 15, right hand. 15 to 20, right hand. The distance between 4 and 7 is 3. 7 to 12 is 5. 12 to 15 is 3. And 15 to 20 is 5. Okay, so these are the widths and the heights of your rectangles. Find your little areas individually. I know that when we did our subintervals on the graphs, we were able to factor something out. We are not able to factor anything out of this problem or anything on this page because all the widths of our rectangles were different from each other. Okay, let's get some multiplication. -15 minus 50 minus 6 plus 40 is -31. Okay, let's go ahead and talk about negative area here for a second. You cannot have negative area. The negative just indicates that the area that is shaded in is below the x-axis. So the area itself is not negative, it's below. And it helps us find specific things for word problems especially. But the negativeness of this does cancel out some of the positiveness of this. Okay? Just do the calculations for now. Don't worry about it. D, approximate from 0 to 25. So this is the whole way across using 3 subintervals. Okay, so we have to divvy this up a little bit differently. Okay, looks like we can go from 0 to 7, 7 to 15, and 15 to 25. So we're skipping over the 4 to 6, the 12 to -10, and the 28. We just care about the base heights. Remember this trapezoid, the bases and the height of the trapezoids, which looks like this. So we care about both y values and we care about the change in x. Both y values, change in x. All right, A equals 1/2 times, oh, we got to figure these numbers out. So we're using 15 and -5. 15 plus -5. And we also have to multiply times the distance between 0 and 7, which is 7. Plus 1/2 times For 7, we're using -5. For 15, we're using -2. Times the distance between 7 and 15, which is 8. Plus a half times. That half doesn't come from like a distance or anything. It comes from finding the average between your two y values. All right, so 15 is -2 plus 20. And then the distance between 15 and 25 is 10. There we go. So for example, on this last one, the -2 and the 20 are the heights of the bases, and then the 10 is this distance right here. All right, well, let's work it out. That 1/2 could absolutely have been factored out because it shows up in every single one of these. So it's your choice if you want to factor out the 1/2. I'm going to go ahead and do that because that means less work. All right, 15 plus -5 is 10, and 10 times 7 is 70. Plus -5 plus -2 is -7. -7 times 8 is -56. Positive 18 times 10 is 180. So I get 194 times the 1/2, which means divide by 2. I get 97. Okay. So you can use any of those formulas. Just figure out how many subintervals you have. What are your shapes? And then do you care about the left? Do you care about the right? Do you care about what's in the middle? Or do you care about, for trapezoids, both of them to find the average between them? And that's how you do these problems. These show up an awful lot on the AP exam, and that's because they're really easy to make up. These problems are super easy to just come up with and come up with a new one for every time they take the ACT. So get good at these.